This is the last of the three-part series on MPI, and Dr. T.K. Panda could not be here today because he has a previous appointment, so he had to go back home. I'm going to be covering the entire session today. So before we begin, I just want to give a quick recap of what we have discussed over the last 2 days, and then we can start our presentation for today. So on the first day, we saw that that there has been a significant amount of progress in designing petaflop systems, and several of them are already deployed. Many of them are using InfiniBand and so on. And at the same time, like the commodity, like the community is going towards multi-petaflop systems, and several 10 petaflop and 20 petaflop systems are on the horizon, and some may use InfiniBand. We also saw that over the last 10, 15 years, if you mine the top 500 data, you will see that clusters have come into this HPC world in a very big way, and they are slowly displacing the massively parallel systems, while the top end of the HPC segment is still dominated by the massively parallel systems. Even then, the commodity clusters are coming in there, and of course, the shining example is the #1 supercomputer in China, which is basically a cluster with NVIDIA GPUs. And we also discussed that MPI has been the dominating programming model for the last decade or so, and despite its limitations, it is indeed widely portable, and you get very good performance out of it. It may be sort of hard to program, but at the same time, this is the best the community has done so far. And there's now we are doing research into better programming abstractions and so on. We saw the MPI-1 and the MPI-2 standards, and what are the basic operations. We went through the semantics of some of the important operations and gave some examples of how they could be used. And then on day 2, we sort of decided, let's go to the day 2 slide. So we looked into what are the design challenges in designing an MPI library, which is capable of executing on a petaflop class system. And we have presented main results from the last 8 years of research. And these were taken from research ideas and from papers and so on, and put into the production code base of MVAPICH and MVAPICH2. And they are being used widely in the world today. And especially on day 2, we saw that MVAPICH and MVAPICH2 have a lot of components. And several of them are quite important for your end application performance. But it also takes some understanding to tune the library for your exact needs. And this is in part because it is a generic purpose library. It should work for a wide variety of applications. It's been tuned for a general application characteristics, which we take from application kernels like NAS, like the Lawrence Livermore applications like the Sequoia benchmarks and so on. But depending on your application, you may want to tune it further, and that's where some of the complexity still lies. And as Professor Duato and I were just having a discussion that how hard it has become to tune things from the lowest level, from the fabric level, like the stuff he was talking about. It takes several months to just tune the congestion management of 2 switches, and here we are talking about a 5,000 node cluster with your fabric, with your software libraries, and then on top of that you have the application, and then then Mrs. Richa Rastogi just talked about how the application needs to handle such a huge amount of data. So I guess there is a lot of complexity, but each of these layers provide some sort of tuning frameworks, and we just need to understand what to tune. So let's start today's presentation. So first, we will look at the challenges in designing exascale systems, and then we'll take a look at what's happening in the MPI 3 domain, like what are the new shiny cool toys you can play with, and hopefully they will be available in the near future. And then we'll spend actually most of the talk in some of the new features which we are trying to incorporate in MPI 2, and these features are sort of like geared towards your multi-petaflop and upcoming exaflop systems, and we think that these are going to be very critical. So we are going to discuss about collective communication, because that is the key to scaling your communication on very large clusters. Then inside this collective communication, you have different aspects like the network offload, and Gilad talked about network offload, I think yesterday, or the day before. And then there's this new feature of MPI, which is called non-blocking collectives. So a collective operation is a blocking call currently, takes a very long time to execute, and the applications are basically stuck until the entire collective is over. And even though you try to optimize this collective, you cannot overlap computation and communication. So we'll take a look at new results from our design of non-blocking collectives and network offload combined. Then we have another important aspect, which is the topology of these clusters. These clusters have become so big that, and the jobs are scattered all over the cluster, that like the collective algorithms need to be aware of where the processes are and intelligently choose an algorithm. Finally, so the collective algorithms should also take into account power consumed. And actually, there's a very nice tie between the congestion management, which was discussed earlier today, and the power consumption and of the end application. And we'll see some results which will actually prove this point. And then we need to, and of course, like a recurring theme over the last 2 days has been the rise of GPU computing and basically how to address this. Sadaf made a presentation about a transparent GPU communication, and over here we'll see how you can basically transfer data using MPI library from one GPU to another GPU without writing any CUDA code at all. So it is at least trying to help the programmer in the sense that you don't have to do CUDA mem copies back to main memory and so on. And this has a tie with the GPU direct. And over here we'll see that we can not only improve the transparency, but also improve performance at the same time. So the first three are very closely linked with the MPI. And the last extra feature which we'll try to discuss about in the context of MPI 2 is the support for UPC and PGAS. So Richa was just talking about how hard it is to program these MPI codes, and you have to deal with CUDA and so on. So there's an effort going on in the DARPA HPCS program, which was to improve the programmability of these parallel applications. So UPC is one effort towards that. It's an extension of C, and unfortunately, like the way the things have happened in the last 10 years, UPC design and implementation has evolved separately from MPI design and implementation. So over the last 8 years, we've just shown what are the communication-related things which you need to tune for MPI. So now if you think about it abstractly, these requirements are actually independent of the programming model themselves. Either you use MPI or you use UPC, you still have to worry about congestion management. You still have to worry over how many rails you have. You still have to worry about what collective algorithm you have to use. You still have to worry about how many cores are there on one node, and so on. So really what we are going to discuss here is that how can we take all the existing research from the MPI world and apply it in a meaningful sense in the UPC and the PGAS world, and have both these models coexist peacefully. And what this will allow people to do, especially this is something which is geared towards the application scientists, is that if they have like a legacy code, right, and you don't want to rewrite this entire code in UPC or some other new language, because that's just cost prohibitive. Like people don't have time to just sit down and just say that, today I'm going to reprogram this in some other language. So here what we want to enable is incrementally changing bits and pieces of your application to use UPC or PGAS. So this will actually provide a very easy and friendly path forward and not block all progress on the programming model front. And after that, we'll talk about some future plans about the MVAPage2 code base and so on. And then finally, we'll conclude. All right. So what is Exaflop computing? So Exaflop computing is computing 10 to the 18 floating point operations per second. That's a lot of floating point operations. And that's exactly 1,000 times of the current state of the art. Now we can do 1 petaflop. Somehow, in the next 6 years, we are supposed to do 1,000 times more. I don't know if we are going to be able to actually reach there, and that actually remains to be seen. Some people are saying that this deadline is going to slip. But I guess only time can tell. But the key intuition, and this was actually highlighted in an IEEE Spectrum article by Peter Kagi, is that Exaflop computing is not particularly just to compute 10 to the 18 floating point operations per second, but it's actually to spur research into power-aware computing. And he gave a very good example that it's not about building a massive computer, but it is really a problem of shrinking a petaflop computer from the size of TNA1 to a size of a refrigerator. So if you can do that, then you have Exaflop computing, and you don't really need to think about in the sense that what are we going to do with all those flops and where the data is going to come and so on. So we need to discover new technologies in computer science, and what these are going to do is enable new class of science where things were not possible to do, or like some simulations were just too hard to do. And maybe we'll prove P equals NP with Exaflop computers. So the DARPA Exascale study has laid out this kind of a roadmap that what needs to happen in the next 6 years now to reach Exaflop computer, and what that computer will actually do for us. So this is just reproduced from that, is the DO Exascale study and Professor Ajak Dongara. So like now we have 2 petaflops, and now we want to go to 1 exaflop. Of course, the power budget is the main thing, which is we only have about 20 megawatts. We don't know exactly how much the Blue Waters is going to take, but which is going to be a 20 petaflop computer. But I've heard estimates of it. It's much greater than 6 megawatts. Then, huh?
I've heard 25.
Oh, all right. Then it's 25 then. System memory will go to 30 to 64 petabytes. It's a lot of memory. And of course, from yesterday's talk, you can just ballpark these numbers to see how hard it's like an order of 100 more. Another interesting thing which we need to see is that this line, like the total concurrency, now we have 225,000, and we are thinking of order of 1 billion threads. And why do we need so many threads? Are there going to be 1 billion cores? Maybe. But I think a key reason to have so many number of threads is that you want to overlap all your computation and all your latency for doing memory accesses, because now we have so many stages in our memory hierarchy, from your register, cache, a main memory, and then you have your multiple layers of storage. Really, now people are even thinking of putting in SSDs and so on in between. So there's such a lot of levels that you need to overlap a lot of things. So it may be that you need about 1 billion threads to keep all the parts of the system active at the same time. And the challenge this will bring to the application programmers is that now you have to manage 1 billion threads. We are only managing about 200,000 threads now. So the application programmers need a lot of help to sort of decide how, what's a good model to actually exploit this kind of parallelism. And of course, the I/O rates are a huge increase. I mean, I don't really know if we can get there, because even currently, on like petaflop computers, I/O is a very big challenge. And of course, the days between failures is going to be order of 1 day. So if the entire computer fails every day, so we cannot think of doing anything meaningful. So the fault tolerance needs to be a critical thing. So as was just also pointed out, that these supercomputers require a lot of energy, and the power consumption is not only for the computation, but also for the memory, other devices, network, and so on. And then on top of that, you need power to cool this damn system. I mean, that's like rubbing salt in your wounds. That first you have to spend so much power to get things going, and then you have to cool it down. So it's already very high, but the cap is about 20 megawatts, because we can't really afford a nuclear reactor for an exaflop computer. So what are the real fundamental challenges in trying to build an exaflop computer? So this was the topic of a report done by Peter Coggy. It's a DARPA Exascale report. So they have laid down these 4 fundamental challenges. So the first challenge of these is the energy and power challenge. Over here, they make a very key observation, is that it is possible to actually reduce the power consumption for compute down by shrinking the size of the transistors, using new fabrication methods, lowering the voltage, and so on. But the energy requirements for data movement is very hard to do, and that is really pervasive, and it was not addressed in a proper manner in like any of these other programs that have been going on. So this is really a very hard thing to do to actually achieve. And then, of course, like the memory and the storage challenge, we have very high capacity requirements, but we are limiting the rate at which we can access each of these devices. So that's very hard. Of course, the locality and the concurrency challenge, which I just talked about, you need 1 billion threads to sort of exploit all your cores, exploit all the various levels of memory hierarchy, network, and so on, and sort of hide these latencies. And then finally, we have the resiliency challenges. Like, if your computer goes down once every day, then you have to deal with it. And this is also linked with the power challenge, because if you have low voltage devices, then they have different failure characteristics all of a sudden. So now they fail more often, and then you need to deal with that. So naturally, the next thought is that what is MPI going to do, right? Should we just leave MPI and think about something new? And I felt like I should put together this slide to see how MPI is planning to address each one of these main challenges. So the power required to move data is the key one for MPI. So over there, what we are going to do is the MPI forum is working towards like non-blocking collectives, and a draft of this has already been voted in, so it's likely going to make the standard. So what this will allow you to do is really hide the cost of expensive, power-hungry collective operations with useful computation. So over here, it will improve the first requirement, which is the power required for data movement. Secondly, there are power wastage when unnecessary synchronization is required between sending and receiving ends. So suppose like a side effect of an algorithm or an internal protocol is to synchronize the sender and receiver, then you're wasting power to actually synchronize, and then you're wasting power by not doing useful computation. So to the extent possible, these programming models and their implementations should completely reduce this need for synchronization. And I think over there, the one-sided interface is going to actually help a lot by actually allowing the programmer to express a pattern in which there is no synchronization involved. Thirdly, we need to manage concurrency, and the way to do that is not to try to contain everything within MPI itself, but also encourage other forms of parallelism, such as OpenMP, UPC, and so on, global arrays, and many things are there, Silk, work stealing. So you don't want to completely restrict everything to MPI. So you have to improve your interoperability with other programming models. So the current one-sided interface in MPI 2 is not very conducive for that. And the improved version in MPI 3 is going to improve the interoperability with these PGAS languages. So that will help towards managing concurrency. And then finally, for the resiliency and like detecting and managing failures, the state of the art in MPI is that if one process crashes, so does the entire job, because the state of MPI becomes undefined as per the specification. So the MPI 3 forum is actually thinking of introducing an interface by which you can detect failures and react at the application level. Okay, so the next set of slides is going to go down slightly deeper into each one of these MPI features which we just discussed. So the three features are the non-blocking collectives, improved one-sided model, and improved fault tolerance. So first we'll take a look at the non-blocking collectives. As I already mentioned, that collective operations are expensive. You need to hide the latency of that with computation. And if you read your MPI collectives carefully, that not all of these collectives are actually synchronizing. Like, for example, if you call MPI all reduce. MPI all reduce is just supposed to compute the data. It's not supposed to synchronize. But actually, it is used sometimes implicitly for two things. In the real application, it can be used for compute, and it can also be used for a barrier, right? So you know that everybody has reached that. So we really wanted to remove this, decouple this. You can still use your blocking version, like if you have a legacy code, and if you want to have a dual effect of compute and synchronize, you can still use that. But in case you have algorithm which is latency tolerant, and you want to remove that synchronization requirement, you can just use the non-blocking version. And of course, barrier is an exception. Barrier is always synchronizing. And now we have a non-blocking version of the barrier, I barrier, and then you can do compute, and then you can finally wait. So the completion semantics of the non-blocking operations is the same as for other MPI collectives, is that it is complete when the local part is complete. So each process only sees its own part in the collective. And the completion of one non-blocking collective does not imply completion of other non-blocking collectives. Suppose you have called like several in a row, like, all to all reduce, and so on, non-blocking versions of these. And if one of them completes, it does not mean that the other one is completed. You have to wait on the MPI request that was returned to you, and they may complete out of order, in fact. And there is no tag for the collective operation. We don't want to match things over and over again, and it becomes very complicated. And this is this is the same with the MPI blocking operations, in fact. MPI blocking collectives also do not have tags. So what can happen is that an application can actually issue a lot of non-blocking collectives. And it is possible to exhaust MPI resources, system resources, so on. Suppose if you start like a million non-blocking collectives, maybe you'll run out of buffers. But the burden is put on the implementation that, like a quality implementation, should not return an error that we could not complete this non-blocking operation. And it should only happen for pathological cases, like inside a micro benchmark or something which you write to deliberately cause this, and not in a real application pattern. So another restriction which was put was that non-blocking calls should not match blocking calls. Like, for example, if you have 4 processes, one of them cannot call I all to all, and the others call all to all. This is a restriction the MPI forum felt was required because the MPI internally may use different algorithms for doing implementing a non-blocking version and a blocking version. So if you did not have this restriction, some application developers could expect that these things will match. And then that means that the implementation will be less efficient, because now it has to deal with this matching stuff. So the blocking implementation of a collective may actually be optimized for latency a lot, right? Because it's a blocking call, applications are waiting, so it's optimized for latency. But the design criteria for non-blocking collectives is completely different. It's for overlap. And as long as you have overlap, you have a great non-blocking collective. It may not be the fastest one, but it needs to consider other things like CPU consumption and how many threads do I need and so on. And another important restriction is that the user must call these collectives in the same order. Like, for example, you cannot call I all to all, I all reduce in one process, and on the other process you call them in a different order. This is because we don't have tags in the collective. We don't do matching of collective operations. Go ahead. I'm sorry, I couldn't hear the question.
So if you have blocking and non-blocking collectives, does the order, is the order important?
I think that, so the question is that on one process, if you call a non-blocking collective and then a blocking collective, and then on other process, can you call the blocking collective and a non-blocking collective? I believe the answer is yes, but I'll check again in the specification to see. Because from the implementation point of view, I don't think that these things should match. Because the non-blocking one will never match the blocking collective. And the fact that the non-blocking collective can always be delayed till the blocking one matches. I think that the implementation should be able to handle this, but I can check and verify that for you. So the progress rules for the non-blocking collectors is the same as that for blocking collectors, which means that when you call a non-blocking collector, it's just a request for doing this operation, and the MPI library is free to delay this for any amount of time, maybe until you call wait, which would be a terrible implementation of the non-blocking collective, but nevertheless, it is allowed. And some examples of new calls are like MPI I barrier, I already use, and so on. We have this I thing in front of everything. So, okay, so now we want to quickly recap one-sided communication. So we had discussed this on the first day, but since it's not a very commonly used feature, I just wanted to quickly recap it. So in one-sided communication, what happens is that you have, suppose, a number of processes. Each contributes a part of your memory, of its own memory, and forms a global window of memory. And now this window can be accessed by each process separately by using MPI put, get, and so on. And it enables you to write the patterns which are irregular, that it's not a request response sort of thing. So it's easier to use for those patterns. And it also decouples data movement with synchronization. So you can issue a whole bunch of get, put, accumulate, and so on, and they can complete in all kinds of orders. Like the order of completion of any one of these operations is not defined. And they're guaranteed only to complete when you actually synchronize. So this enables a lot of optimization within the MPI library for efficient use of network, memory, cores, so on. And finally, from the application point of view, the foremost reason you want to use this is that you have direct control over overlap of computation and communication. If you use MPI I send, I receive, that may still have some problems, because MPI I send and I receive will still have to match the messages. So that requires a two-way transfer. So that's still an implementation issue. But for one-sided, it should be very clear for the implementation. And a good implementation should be able to overlap everything. And yesterday, we actually presented our MVAPH2 version of the one-sided implementation, and we also showed numbers to prove that it actually does overlap computation and communication. So what's new with the recap in mind? What's new in MPI 3? How are things better? So first, as a quick definition, this MPI 3 one-sided access is also called as remote memory access, or RMA, and sometimes these two words are used interchangeably. Like RMA can be used for one-sided and so on. Before we go into the new stuff, I just want to quickly introduce another a little tricky concept in MPI one-sided access, and let's see what these are. So we have a concept of two windows. So window is a global memory which is contributed by each individual process giving some of its own memory. And logically, there are two windows. One is a private window, and the other is a public window. So the public window is what is exposed to other processes. So when like a remote RMA operation is coming to this window, it goes into the public window. And then when you actually synchronize these two windows by calling MPI fence or lock unlock or active synchronization, there are multiple ways of actually synchronizing. When you actually do synchronize, the effect is that these private windows and public windows become the same. So the contents are synchronized. And then finally, after the synchronization is over, then the processor can locally read write from that. And Of course, like naturally you might ask, why is all this required? Why don't I just write directly? Why is a model like this? It's because it needs to work for non-cache coherent systems. Suppose your one-sided window is actually on a GPU, right? Then what happens? Like if you issue MPI put, then will your GPU be able to, will be able to like read it directly? Because the GPU doesn't have MPI rank. So you will be issuing an MPI put to a rank, like an MPI rank. So this buffer may actually be sitting in your main memory of the remote node and not necessarily on the GPU. So if you look at it in one way, it's a non-cache coherent system. You need to explicitly synchronize the main memory on the remote node with the GPU memory on the remote node. So once these things are synchronized, then the GPU can read and the main the main processor can read and so on. So while this MPI2 definition of private and public window works well for non-cache cache coherent systems, but it's not very efficient for the systems in which like your hardware will give you cache coherence. For example, like a normal commodity node, Intel Westmere with Mellanox InfiniBand, right? This means that like whenever a remote DMA occurs in your main memory, it is immediately available for the processor for reading, because it is actually cache coherent, because those lines would be evicted from the cache lines and so on. So like your memory controller will actually deal with this. But the MPI model does not expose this. So it's not very efficient. You have to wait till, for the synchronization and so on. So instead, in MPI3, what we have done is we have two types of windows. One is a unified window, where it is assumed that these two are the same, and the machine is hardware cache coherent, and the other is separate, which is the same as the old concept where you have public windows and private windows. So if you have a unified window, then you can effectively leverage your hardware cache coherence. Any questions in these previous slides? Yeah, go ahead.
What if the customer wants to implement the non-coherent shared memory machines?
Yeah.
MPI2 semantics will still work.
Yeah. So the question is that does MPI2 work for non-cache? In fact, it's meant for that. So the non-cache coherent systems were like a lowest common denominator, so to speak. Although mathematically that term doesn't exist, but it's like used in this field very well. So they are, but it's not good for like systems which have cache coherence. So that's why we want to introduce. So Brian tells me I have only 1 more minute. So I'll quickly describe the new MPI3 calls. The new MPI3 calls are MPI win create dynamic, where you can create an MPI window but not attach any memory to it immediately. And that's required for PGAS languages, where they may want to access a large amount of shared memory window but not give up all, like if you have a 64-bit address space, are you really going to allocate a 64-bit address space? Likely not. Like you just want an abstract notion of a global window, and then you'll attach specific address ranges to that. So that's now possible. What else is possible is that you have local completion with a request put. So you issue a MPI put, but that returns back a request. And then you can wait on the request just like any other MPI operation, MPI wait, right? And what that is going to do is, when that request completes, you're guaranteed that it completes locally. It may still be outstanding in the network, but at that point of time, you can like reuse your buffers at the sender side and so on. And the same things for get and accumulate. And then finally, you have these new calls called get accumulate, which is basically like a remote compare and swap, right? You get you accumulate some data at the remote side and return the old data back. So these are like your atomic operations which are commonly used, and these are just general versions of that, right? Which accept data types and all kinds of things, and then you have variants of this, which is MPI fetch and op and compare and swap, which have limited argument list and so on. So this just allows the MPI implementation to have a faster version of that. Not necessarily conceptually different, but the concept is that now you can do compare and swap with MPI, which was not very easy to do earlier. So with that, we can take a break now.